So in the lecture before last lecture, we discussed subbasis for a topology on X. So subbasis, we know that is a collection of subsets of X whose union is the whole set X. If this condition is satisfied, then we call the collection S alpha to be the subbasis of X. And once we have a subbasis for a set X, we can generate a basis using by taking the all possible finite intersection from this collection S. So once we get a basis from subbasis, then we know that how to generate the topology. So if I have a basis, then I can take all the possible unions of elements of B, and that is the corresponding basis. So this is regarding the previous lecture, and in the last lecture we discussed product topology. So if X and Y are topological spaces, then how to define a topology on X cross Y? So as we know that every topology is we can get a topology from a basis. So if X has a topology tau X, Y has a topology tau Y, then I can get, using tau X and tau Y, I can get basis on X cross Y. So what is the definition of basis? It is the collection of sets U cross V, where U is element of tau X topology on X and V is a element of topology on Y. I will take all such cross products. So collect all such sets U cross V, where U belongs to tau X and V belongs to tau Y. That will give us a family B, and then we have verified that B is basis for the set X cross Y. And once it is a basis, it will give us a topology. Every basis on a given set gives us a topology. So the topology generated by this basis on X cross Y, that we call product topology. So this is a product topology on X cross Y. So that means whenever I have a topology on X and topology on Y, using that two topologies, I can define topology on X cross Y. So that is this product topology. And later on we discussed that so basically this is the definition of product topology on X cross Y using the elements of tau X and tau Y. We are taking all possible unions of the basis elements. On the other hand, if I have a basis for the topology on X and basis on the basis for a topology on Y, then I will get another basis on X cross Y. So instead of taking U cross V, where U and V are elements of tau X and tau Y, we are taking B cross C, where B is a basis element on X and C is a basis element on Y. C is a subset of Y, which is a basis element. So all such sets we will take. And we have verified that this is also a basis on X cross Y. So the two axioms of basis are verified. And then we discuss whether, so now we got two bases on X cross Y. So whether these both bases generate the same topology, which is, we already know one basis generated topology, which we call product topology. The other basis generates a topology, whether it is same as this product topology. So that is this question. So this I have suggested that you can do using this and this result which we have discussed when we discuss the lower limit topology, right? So any question in so far?
Sir, this exercise, are you going to solve it or we have to solve it?
So obviously exercise should be solved by the students.
Okay, sir.
So you try it. If you are not able to solve, then I can help. But without you try, how can I solve? So first you try that using this definition. So let me give you a hint kind of thing. So for example, this is a basic result which helps sometimes to prove this type of exercises or results. So if I have, for example, two bases, so B is a basis and B dash is also basis on the same set X, right? Now presently I'm not discussing product topology. I'm just taking a B is a basis on some set X and B dash is another basis on the same set X. So that means I will have two topologies. One is generated by B that we denote by tau B. Another is generated by B dash that is tau B dash. So if I know that this base is all basis elements, that means elements of the collection B is subset of the collection tau B dash. If I know this, then I will get tau B is contained in tau B dash. So is it clear this result is true? In fact, it is obvious, but for example, how to prove this result? Any idea about that?
We have to take the element of tau p, then and tau p, then basis would be b. Then we
So,
will use
so
the
what is
basis definition.
yes? So what is the definition of tau b? Can you recall?
All possible unions of basis b,
Yeah,
basis
right,
elements of b.
correct. So here, proof is quite simple. So what is tau b? Tau is b is nothing but union of alpha b alpha such that, so as you said, it is b alpha belongs to b. So this b alpha is basis element. We are taking all the possible unions of the basis element of B. So in particular, we know that basis is contained in tau B, right? Because if I take only one union, B alpha, I'm not taking any other set, only single union. So that is also contained. So, so if I know that this B is contained in tau B dash, so then what can I say about union alpha B alpha? Whether it is contained in tau B dash, I should write belongs to. So is it true? In fact, it is true. So which property we are using here? That is the question. So if I have a basis collection of elements, so what is B? B is the collection of subsets of X that satisfy these two properties of basis. On the other hand, I have a tau b dash, which is a topology. So what is meaning of topology? It contains phi, it contains x, and it is closed under arbitrary union. It is closed under finite intersection. So if I have this, then this condition follows. So how this follows, whether I am using property of basis or I am using property of topology.
Using property of topology, because the B alphas belongs to eta and B, and B is a subset of tau beta dash. All B alphas will belong to tau beta dash. So
Yes, so
I
which
will take
property, basic union property we are using, right? So that is what you said. So basically we know B alpha is a basis element. So that means from this B alpha belongs to tau B dash, and B alpha, each B alpha belongs to, let me write here because it may not be clear. So what we have is B is contained in tau B dash. So if I take any B alpha belongs to B, then what I will get, because of this condition, B alpha is also in tau B dash for every alpha, right? Because B alpha is element of B. So using this, we are getting this. And then we know that tau B dash is a topology anyway. So that means it is closed under union, right? So for all such collection B alpha, this is true. So that means, and what is tau B? Tau B is nothing but union alpha B alpha, where B alpha belongs to B. So every such element belongs to tau B dash. So this is a subset of tau B dash. So what we use is we use only that tau B dash is a topology, and this topology is closed under union. Every topology is closed under union. So this is just simple result which we can use. So once again, what is the result? The result is that if I have a family B and B dash which are bases on X, and if I know one basis is contained in other topology, right? One basis is contained in the topology generated by other basis, then the topology generated by this basis is contained in tau B dash. So this result you can use to prove one part of this exercise, and the other part is trivial, right? So just try this exercise, then after you try we will discuss. Okay, so one example I want to take here, because in product topology I have not discussed any uh, concrete example. So product topology is a topology on X cross Y, right? So if I take X to be R and Y also R, right? I can take, because X and Y are any arbitrary set. So then what is tau X cross Y? Uh, in fact, basis for the product topology. So basis, if you recall, it is U cross V. So what is the definition of product topology? It is generated by U cross V. U belongs to tau X and V belongs to tau Y, right? So Basically, we have two sets U cross V where U belongs to tau x. Now x is R and V is in tau pi. Y is R. Right, this basis for the basis for the product topology on R cross R. R cross R means basically R2. Right. So we are in XY plane situation. Further, what topology on R I am taking? I am taking standard topology. So let tau R be the standard topology on R. So now what is this uh, Vx cross Y? Vx cross Y in this case is U cross V, where U is open subset of R. So open subset of R means real analysis science. Basically V is open subset of R. Right. Similarly, what will be the other topology? So if you recall so what the exercise says, what the exercise says, both these bases generate the same topology, right? So here answer is yes. So you can check this. So if I have the basis D or I have uh, the other basis U cross V, they generate the same topology. Tau D is basically tau V, right? So if I want to use this result, which I have not proved, then what it says? It says that the other basis is D equal to B cross C, where B and C are bases of X and Y respectively. So on standard topology, what is the basis? Yes. What is
प्रोडक्ट मेरे को तो रेक्टेंगल बन जाएगा.
uh, that is correct, but I'm not asking. So you have given the correct answer in R2, but I'm asking in R. What is the standard basis in R?
Intervals, open
That is
intervals.
interval, right? So here basically B and C are intervals, open intervals, precisely in R. Correct. So then what you said is correct, that if I take V is interval, C is interval, then B cross C is the rectangular region, right? Because here I take interval, here I take interval, then B cross, this is my B basically, this is my C. So B cross C is somewhat of this form. So earlier we have drawn rectangle kind of thing, and inside rectangle, all these points, right? because we are taking open intervals. So boundary of the rectangle will not come. So this is B cross C. So as many open intervals B and C we have, as many rectangles will be there as an element of this collection. So question is that is the product topology on R2 coming from the standard topology on R? So that is exactly this. So this we know from that exercise that this is the basis for the product topology. This is a basis for the product topology on R2. And on the other hand, what is the basis for standard topology on R2?
उसमें रेक्टेंगल्स होता है या सर्कल सर्कल
Yes, what is the answer?
rectangles and circles.
No, that are two different topologies. So one is the topology generated by rectangular regions, and the other so we discussed two bases on R2. So one is the basis which is collection of all rectangular regions. The other basis is all the collection of circular regions. But I think I have mentioned that when we discuss standard topology on R2, so that means we are discussing analog of intervals. So that is the rectangular, circular regions. So collection of open disk basically. So that is the basis on R2. So let's see be the collection of all circular disk in R2. Then we know that C is the basis for the standard topology on R2, because from the real analysis or multivariable analysis you can say that every open set in R2, if it around that point we have a small disk which is contained in that set, so therefore it is called standard topology on R2, right? So question is that this is also topology on R2, this is also topology on R2 which is generated by this basis, whether these two topology are same or not. So that is this question, that is the product topology on R2 coming from the standard topology on R equals the standard topology on R2. So so we know
सर
that
जो आर आर क्रॉस आर को आपने आर टू लिख दिए हैं वो क्या सेम ही होता है आर क्रॉस आर ये वाला
R
कैसे
cross
करते हैं
R cross R
आर
means two coordinates of real number.
नहीं ऐसे तो पता है वो होता है ऊपर ऐसे लिख सकते
uh,
हैं कि आर क्रॉस आर इज आर
as a,
टू
as
या ये
as,
नोटेशन है या कुछ प्रूफ
as
है
a
इसका
said, so
ये
what is
वाला
Rn?
ऑल टपल्स होगा ए एक और वन कॉमन
So this is nothing but I belongs to R, I belongs to 1 to n. So this is same as R cross R n times.
तो ये बस नोटेशन यूज हो रहा है
Yes, this is called the what we call coordinate space or whatever. What is x cross y? X cross y is just xy, so that x is in x, y is in y. This in every course we are using it,
यस
right? This is standard notation. Actually, it is coming from school mathematics, Cartesian plane, basically. Cartesian coordinate or whatever you call. So we want to prove that the topology generated by this is equals to the topology generated by this basis open disk. So have we verified earlier this thing? So as you said that one basis elements are rectangular regions and other basis elements are open disk, circular disk.
Visually, we have done one things previously finer than e- each other. तो उसमें दोनों equal हो
Yes,
गया था.
at the time we have already compared the topology generated by these two bases. So therefore we already know these two topologies are same, right? So we already checked that these two topologies are same. When we, as you said, when we compared the finer and weaker topology, that notion at the time we discussed. Just 1 minute. Okay, so so this is what regarding this topic. Now next I want to discuss projections.
तो इसका सर कोई प्रूफ ऐसा नहीं देंगे, वो जियोमेट्रिकल प्रूफ ही सफिशिएंट है.
Because this is based on the shapes. So earlier also I said that this is only geometrical proof is required here. But if you want to prove, then you can prove using that epsilon ball. You can take two epsilon and you can take minimum of them or something. That argument also you can give, but geometrical is more transparent and visible. So there is too much rain today. I don't know why. So this we know the projections map. So the projection on X I will denote as phi1 map, and let phi2 be the map from X cross Y to Y defined by phi2 on XY defined to be Y. Then this maps phi1 and phi2 are called projections from X cross Y onto X. So here onto X means it is a its image is whole X, range is whole set X, and for the second map it is onto Y respectively. So so if I take any open set in X, then what is phi1 inverse U?
X comma y order here.
So it will be a strip actually.
या वी मतलब वो पता नहीं रहेगा हमें क्या उसका जो एक्स का मैपिंग तो पता रहेगा पर वाई का मैपिंग पता नहीं रहेगा।
So for example, we can draw the diagram also. So if I have like R2 plane, so this is my x-axis, this is my y-axis, and open set. Let me take this is my u, right? So then, what will be pi one inverse u? That means what points in the xy which I can project on u. So can I project this element?
यस।
I can project, right? So basically, if you recall or you check the geometrically, whatever points are here, its x coordinate belongs to you. So that is exactly the meaning of the this pi one map. So pi one inverse u is you can verify later on also u cross y basically. So what is this set? This set is nothing but u cross y. So what is pi one inverse u? Pi one inverse u is basically the points x and y, such that pi one of xy belongs to u. And so what is pi one of xy? That is x belongs to u, right? Because pi one of xy is x. Sorry, pi one of xy is x. So similarly, so can I discuss pi two inverse u?
यस।
But pi two is a map whose codomain is what? It is not x. It is actually y. So basically, I have to take the open set in y, right? Not in x. So that way, this is not correct. So I have to take the open set. Let v be an open set in y. Then what will be pi two inverse v? That will be similarly. I can write it is a x cross v. So you can verify these. So in the same figure, we can also discuss this. So if I take here v, then what will be the points which I can project on V along y-axis. So they are all these points, right? So all these points I can project on V. So what is the intersection of these two sets? That is this one. And what? Yes.
सर ये जो रेक्टेंगुलर रीजन आएगा वो का इंटरसेक्शन।
हाँ, that will be rectangular based on. So यहाँ पे तो मैंने फिगर में actually similar kind of interval लिए है. So it looks like a square, but as you said, it is a rectangular region. So what is the intersection of pi one inverse u and pi two inverse v in terms of u and v?
यू क्रॉस वी होगा।
That will be u cross v, right? So that we can see from the figure also, it may be square or rectangular, but it is always be u cross v. U cross v means exactly this interior of this rectangle. Okay, so this will lead us to one simple result. It is in terms of, for subbases we did not discuss many results, so this is one of the important result. So the collection S. So let me go to the next next file. The collection S defined to be phi 1 inverse u, where u is open in X, union phi 2 inverse v, where v is open in open subset of Y. So if I take this collection, then this is a, we can check that this is a sub basis because I am using notation S. So you can guess that it is a sub basis for the product topology on X cross Y. So so you just tell me what we need to check to prove this theorem. Proof we will discuss later. So what
काउंटेबल
exact?
यूनियंस करके सब बेसिस तो
Yeah, sub basis we already discussed that it generates. Just a minute. It generates. Hello, am I audible? Okay. Okay. So as you said that if I have a sub basis, then how we generate the topology? So the topology generated by sub basis, we have to take the all finite intersection of elements of S that will give us basis, and then from basis to topology we already know we have to take all unions of the basis elements. So that is the topology generated by this sub basis, and the question here is we have to prove that that topology generated by this sub basis is same as the product topology. So that is this result. So for proof, let us consider tau to be the product topology on the set X cross Y. So that is the topology generated by the basis elements U cross V, and tau dash be the topology generated by S, right? So so as we have discussed this result uh, regarding the basis element, if I can show that every basis element is contained in another topology, then I will get this one, right? So instead of basis here I have sub basis element. So is this result true for sub basis also?
सब बेसिस इज आल्सो a basis, so it will be true.
Every element in sub basis is basis, but actually what I want to ask is that if I have so one, if I have a sub base S and S dash on X, then if S is contained in tau bs dash, then can I say that tau bs s is contained in tau bs dash? So this is also true. So first we can show bs is contained in tau bs dash. Then this anyway we know that if basis is contained in another topology, then this holds from that result. So what will be used here? So we know that basis is coming from the subbasis by taking finite intersection, right? And then we know that topology is also closed under taking finite intersection. So therefore, if S is contained in this, then Bs is also contained here, because Bs is coming as a finite intersection of element of S, and every topology is closed under finite intersection. So the proof is similar to that result. So here we already know that. So what are the elements of S? Elements of S are either this form or this form. And then we know that what is pi 1 inverse. So this is U actually. What is pi 1 inverse U? That is U cross Y, right? So U cross Y is open in X cross Y. Is U cross Y?
Yes.
Yes, it is open because U belongs to tau X, so it is open in X, and Y is the full set. So every topology contains phi and X. So for topology and Y, it should contain phi and Y. So therefore, U also belongs to tau X and Y is in tau Y. So U cross V is U cross Y here. That is open set. Similarly, this is also open set. So every element of S is open in the product topology. So in product topology, U cross X and U cross Y and X cross V are open set where U belongs to tau X and V belongs to tau Y, right? By the definition of the basis of the product topology, these two are in fact basis elements in the product topology. So therefore, and all this, what are these elements? This is nothing but pi 1 inverse U, and this is nothing but pi 2 inverse V. I wrote the pi 2, right? Okay. So pi 2 inverse V. So therefore, every element of S is is belongs to is in the product topology. So what is the notation for product topology? That is tau. So what we got is S is contained in tau, and then from S how we get the topology tau dash by taking finite union, finite intersection and arbitrary union. So therefore, if I take finite intersection, I will get the family Bs that is contained in tau, and then the topology generated by Bs is tau dash, and that is contained in tau. So using the similar argument what we have discussed, we got this result. right? And on the other hand, now what I need to show? I need to show the other way around. Tau is a subset of tau dash. So for that, I will compare the basis element of the product topology. So if I can show that U cross V belongs to tau dash, then I am done. Right? So this is what I need to show. So to show U cross V in tau dash, I have to show U cross V is open. What is U cross V? We already verified. Here, U cross V is nothing but pi 1 inverse U intersection pi 2 inverse V. Right? So this says that, and what we already know that pi 1 inverse U is open. This is open and this is also open. Uh, sorry, these two are the sub basis elements. This and this belongs to S, right? So I can write a set U cross V, every set U cross V as an intersection of basis elements. So that means what? U cross V belongs to basis of S, and basis of S is contained in the topology generated by basis. So topology generated by S is tau dash. So therefore, every basis element of tau is a subset of tau dash, and that gives us tau is subset of tau dash. So we got both the things. Tau dash is contained in tau and tau is contained in tau dash. So therefore, these both topologies are same.
सर फिर से एक बार एक्सप्लेन
So, so this, did you understand this? Why this is true? This proof.
यस आप
So
प्रूफ किए थे
we have basis element contained in the topology generated by another basis. Then the topology generated by this basis is subset of this, because this topology is, every topology is closed under union. The same way we can prove that this result, if I have a subbasis contained in the topology, then topology is closed under finite intersection. So therefore, if I take all possible finite intersection, then I will get basis. So that basis is also contained in this, right? That is exactly this. And then once basis is contained in this, then by this result, we will get the topology generated by this basis is also contained in this topology. Right. So whether I have one basis is contained in other topology or one subbasis is contained in another topology, I can show that both the topology, the first topology generated by first basis or subbasis is contained in the other topology. So the same idea we are using here. So which part did you have doubt?
No, it's slightly confusing. That's why I'm asking to repeat it again.
Yeah. So what part is confusing? Which step?
The proofs actually, sir. This proof, this proof.
Proof, you up to this you already understood that this is U cross V. Where is that basis element? Okay, I drawn in some another slide, maybe this one. So this we already understood, right?
Yes.
So now we already know that this set is open in the product topology. Same way, this set is open in the product topology, because every set of this form U cross Y is open, in product topology, and this is also open. So that is the first part here, that if I take, of course this is not that much easy to understand at first instance, but basically what we are using is topology is closed under finite intersection, and every topology is closed under arbitrary union. So every time we are showing that first we need to show that tau dash is contained in tau. So to show tau dash is contained in tau, I will first show the basis of tau dash contained in tau. So once I show this, this is clear from that result. So to show basis contained in tau, it is enough to show subbasis is contained in tau. Right? Once I prove this, this will follow, because topology is closed under arbitrary finite intersection. So essentially, to show tau dash contained in tau, I have to show subbase. Every subbase is contained in tau. Now, what is tau? Tau is the product topology on x cross y. So to show S is contained in tau dash, I have to show every subbasis element is open in the product topology. So which elements are open in topology? All basis elements. So every basis element is open in the product topology. So that means every set of the form U cross V is open in tau. So I have to show every subbasis element. What are the subbasis element? Either of this form or of this form. And both of these sets I can write in terms of U cross V, where U and V are open. Right, so that will give us S is contained in tau. So this is the first part. And then converse. So converse, what I need to show? I need to show tau is contained in tau
सर
dash.
सर 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 जो ऊपर में आप प्रूफ अभी बताएं तो वो यू क्रॉस भी वहाँ से लेके आए जो ओपन बताएं वो वहाँ का रिजल्ट यूज़ किए जो पहले निकाले थे
हाँ
कि ये यू है और ये वी है मतलब यू
हाँ, ये
क्रॉस वी
U है
है
और V है। हाँ, तो ये
अच्छा
ओपन है, वो तो पता है ना प्रोडक्ट टोपोलॉजी में, ये समझ में आ गया
हाँ
ना।
हाँ हाँ
सिमिलरली ये भी ओपन है, और सब बेसिस के एवरी एलिमेंट इज आइदर of this form or of this form, right? So every element of subbasis is open in tau, that means it belongs to tau basically. So that we have proved here,
अच्छा अच्छा
right? And similarly we have proved here that I want to show tau is contained in tau dash. For that I have to show every basis element of tau. So basis element of tau, tau is the product topology, so basis element is of the form U cross V in the tau product topology. So if I can show this is open for the topology generated by S. This is, so in fact we will show this is basis element, so that is enough, right? Because if I can show it is basis element, every basis element is open in the topology. So to show U cross V is open in S, we can simply have to write U cross V. So what are the basis element in S? They are finite intersection of element of S. So this is a finite intersection of element of S. So it is belongs to the basis, right? So intersection belongs to basis actually, but these both elements are elements of S. So therefore U cross V belongs to basis of S. So therefore it is open. So that is this part, right? So I hope this is clear now,
यस सर
right? Otherwise you can again go through it one more time. That should be enough actually.